So we will use this that we learned what the dipole is to now study more antennas. And particularly we will study what's called a folded dipole, monopole, and then we will look at short antennas, and then we will make a generalization to the Friis transmission formula in the end. In the end of the lecture, I will also start talking about the lab. So next week, we will start the lab. We will push the dates a little bit since we couldn't have the computer exercise yesterday. So you will get more times to do that exercise on Wednesday, and then the design of your own patch antenna. And the patch antenna we will talk about on Monday. So that's a very important lecture. Also on today, the first quiz is closing. So I know I got some feedback on some question. I think it was the accuracy that was setting, so that is fixed. So I do update this question if something is wrong. And this year we have merged this question from another system to the new system, and it might be that there are small parts in them. And if you discover that when you solve the quiz, send me an email, and I will take a look at it whenever I can, and if I can fix it, I will fix it for you. So just contact me if there is something there. Don't get irritated on your computer or anything else, or me or something. Just relax, take your time, send an email, and we will fix it. And the quiz is there really for you to learn. So it helps you in your learning process by repeating these things that I think you should really know from the previous lecture. And I think I'm actually wrong. The second quiz has not opened yet because I haven't put it up. So I will add that one, and it will come up this afternoon. Maybe it has opened formally, but the problems are not there yet. So that will come up later today. Okay. We get the question here of the lab will be online or campus. So next week it will be everything online. So you will do your own design next week. And then week 5 and 6, there we hope that we can really run those labs on campus. But due to this Corona situation, we have to minimize everything with this in-person teaching on campus. But week 5 and 6, you cannot do it at home, so that we need to do at the university. I will talk more about that later. Okay, so what we will do now is then that we will move on here from our dipole. So we will generalize our dipole to, as I mentioned, folded dipole, monopole, and look at a little bit at Friis transmission formula. And then in the end, I come back to this laboratory session that's not next week. So what do you know at the moment? Hopefully you know a lot. You've done the exercises, you've seen the lectures. Of course, we've only gone around 1.5 weeks, but you should basically have learned how to determine the radiation pattern from a given current distribution. Doing this by paper and pen, of course, you can only do it with the simplest cases. So you have computed this for this short dipole, but you have at least understood the big process of this, that on an antenna like this dipole, you get some currents going here. So you have some currents in some ways going forward and back here, or current density J. And that is what creates this radiation that comes out. So this current will produce an electric field. And you have learned how to determine the electric field from the current density by taking the Fourier transform of the current density. It's a very simple formula. And then removing of the radial component. So far away from this antenna, it's a plane wave. And we know that the E and H are perpendicular to the direction of radiation. And that means you have to remove that component. So that part you should have learned so far. You've also learned here what this Hertzian dipole is. So you have this radiation pattern, 1.5 times sine squared theta. And that's basically what is depicted down here. That is one way, and here you can see the radiated field. For some reason, my movies don't run today. I don't know why. Should be a movie there, but it doesn't work. So that you also have learned. So you have an appreciation of this radiation pattern. You should be able to interpret the radiation pattern. You also learned that we went down here to the half-wave dipole. So we made it slightly longer, so approximately half a wavelength long. The directivity went up a little bit, so the maximum directivity went from 1.5 to 1.64, so like 10% up. Not a huge deal, but a little bit higher, that you should know. And the radiation resistance is a quite good number, a little bit more than 70 ohms, typically 70 to 75 ohms. That's the range where it sits. We also initially looked a little bit at the bandwidth is increasing slightly with the width. The width of the dipole doesn't really affect the resonance frequency, it doesn't affect the directivity, but it gives you some bandwidth. And I showed you some simulations. Unfortunately, you have not been able to run them yourself if you're not gone to the lab on the 4th floor. If you go to the lab, you can run them. The lab is open for you and you have instructions to do it. So this is in some ways a knowledge we should have. And now we should take this knowledge and start to understand other antennas. And that's what we will do this, what to say, lecture. That's what we will do next lecture and the coming lectures. So we really build on this understanding. We will use this understanding to understand quite a lot of different types of antennas, which means that it's not only this dipole. Now we will start looking at many different types of antennas. So let's move to some, or where we are in the course. I know I showed you this one on the first lecture. And as you can see here, we have many different types of antenna elements. So far, I mean, we've done those two. Now we will start doing the rest. We basically have done all of these parameters, or most of the parameters we looked at. And in the analysis techniques, in some ways, we looked at these things of going from the currents to the far field. So now we will start filling this. So this is the entire course, but we will start with the small pieces and we will basically move on to expand our knowledge. So this is what you have looked at so far. Not that much from a total covering of the topics, but the really fundamentals we have done now. You should have an appreciation for it, which means understanding, for example, of course, what is gain, what is directivity, what is the efficiency, and so on. These antenna parameters that we talk about. Those you should know. And of course, you should know how this one looks. After today's lecture, you should know how this antenna looks. That's the monopole. We will do that one today. So if we think how I actually introduced the dipole antenna. If you remember back there, I think 2 lectures in this case, or if it was the previous lecture, we took this transmission line that sits here and we say that let's bend these wires up here. And we make those approximately half a wavelength and it makes it radiate. That's how we motivate it. That's how we do the dipole antenna. That's a good way of thinking about it. Your transmission line doesn't radiate, so let's make it a little bit wider in some ways with this wire sticking out, and then it starts radiating. And then we learn these parts that I already said before, like 73 ohms, and you have a directivity around 1.64. But then we also learned that this transmission line here, this case of taking 2 wires and put them next to each other, has a particular characteristic impedance. We have learned that the antenna should fit the characteristic impedance on the transmission line. Typically, we said we have 50 ohms, but this twin wire that we motivated the dipole is not like that. It's typically around 300 ohms. And that comes from the physics of this, that we need to separate these 2 pieces of metal. They need to have some distance d, they have some radius a, and reasonable numbers of this gives around 300 ohms. So this is where we sit with these wires. And now you can start asking, if this is the case for this twin wire, and then I said here, just take your twin wire, bend it up, and you get a good radiating antenna. Is that actually true? Do you get a good antenna if you do like that?
I don't think so.
No? And why not?
It's because we have to be precise.
Yeah, we can be precise. Let's make it around half a wavelength. So we can do it, I mean, assume we can do it with the correct length and so on. Let's assume that.
Then I don't know.
But we have a problem here, because what is the characteristic impedance of the transmission line? 300 ohms. And what was it for your dipole antenna? 73. Is this good?
We're gonna have a problem matching.
Yeah. This antenna is not matched. So there is a flaw in the argument I was using. It's not only me who's using this argument, it's a very good pedagogical argument to a little bit explain how you can do this. But of course, there's a flaw in this because I'm quite mismatched. I will have a large reflection coefficient. I will have a loss. So I have a reflected wave coming back. So I lose power. It doesn't really work. So you can really start asking the question here. Can we match this dipole type antenna to a twin LED transmission line? Can we do it? Or is it just fundamentally flawed? Should I change the transmission line to make it 73 ohms, or can I do something else? What do you think? Probably since I asked the question, we can do it. What do we do to match these ones to each other? I need to change something. Should I change the transmission line or should I change the antenna? Of course, this is a course in antenna technology. So we change the antenna. And that's what we're going to do now. We're going to remake our dipole antenna. So it's not 73 ohms anymore. We're going to change the impedance of the dipole antenna. And what I will show you is a general design trick that is used quite a lot to actually change the input impedance of your antenna. We will make it better, especially in these cases to get to 300 ohms. Of course, you can say like, yeah, in reality, I would like to have 50 ohm and then it doesn't work. But you also learn that we then shrink our dipole. We go down in radiation resistance. And maybe we sit in the same situation, and we do. So now we will see how we can do this. And we will only use knowledge that you already have. So really what you have learned so far, what you have understood so far, that is what we're going to use. And that goes to what's called a folded dipole antenna. So we take an antenna now that I added the word folded. That's the only thing I add. It's still a dipole antenna, but it's a folded dipole antenna. And the trick that is done is that here you have the regular dipole. So you can see it's fed by this transmission line. You have a current on your wire that goes out. But now I do something else here. I add these ones, I follow these ones, and I close it with a loop here. So it goes around like that. And that is what this word folded comes in. So I basically fold the dipole in some ways. I keep the same dimensions here, so it has the same length, approximately half a wavelength. We will only, to start, we'll look at this one at half a wavelength or around half a wavelength. So it's close to resonance. And you learn now that the resonance is slightly off from that, but that we have learned, so we can compensate for that. And I will still call it half a wavelength dipole, even if it's not exactly half a wavelength. And now we will see what happens with the input impedance of that one. That's what we will ask. And what is the input impedance? Yeah, the input impedance here is that you should look at the voltage at the feed and the current at the feed. The sign of this doesn't really matter. So we can change the voltage if we would like to, but think about it with the conventions I put up here. Then it should be the voltage divided by the current. That is the input impedance. And I have the same thing in the right here. I have a new voltage, and that is the voltage of the folded dipole. I claim in the first case I will have the same current. And my question is, how does the radiation resistance change when I do this? Obviously it will change, because otherwise I wouldn't talk about these things. So it will change. But how does it change? And we will not use anything new. We don't do any fancy calculations or anything. Only simple back over the envelope understanding of what's happening in these cases.
Sorry, the question
Yeah.
is question was, how is the resistance is less
Or increased either. Yeah.
Okay.
So that is what we're going to determine. How does the radiation resistance change when I fold this dipole? And it will be a general rule that's valid for many different types of antennas. But here you're going to understand it from really basic principles. And those are the important things to understand. So let's see what's happening in these cases. We sit at resonance. And what we have in these cases is that you have some current here. If you think about your dipole, that is the current I. I have the same current in this wire here, but now when I put these two wires close together, I will actually have the current density both in this wire and in this wire. So there are two current densities next to each other, which have the same amplitude, very close together, because this distance d here is very small. So this much is much less than L. So basically two dipoles next to each other. And I know the shape of that current. It's the same as the half wavelength dipole, approximately this cosine function. That is what I have here. And what does that mean? Yeah, the same current means that I have 2 times the current density for radiation. That is the effect I have. Now I'm going to determine, okay, what is the radiated field from that one? Okay, Khalad, you have a question here, I think.
Yes, can you please show us how can we put two dipoles like this figures in reality? If you have two dipoles and put it beside each others, because here I get confused with the shape of the dipole.
Yeah, so what you have here is actually, if you think about the first case, you know, a dipole was listing. So that is a typical dipole antenna. Now I don't put two of these next to each other. I make the new antenna, which is called folded dipole, that looks like this. So I have the same feed, but I basically close this part here. So I add this piece to it here. I put a new wire there. I will show you pictures of this very soon. It's the typical antenna you will see in all basically Jaguda TV antennas. This one sits there.
Ah, okay.
So it's really that I take my wire and I just make it into a loop. That's what I do. So still, you only feed it at one place, but you take and close the wire around it. That's the trick we are doing here in some ways.
Okay, thank you.
So if I now have this here, okay, I have the same current in them. So I have 2 times the current density. What does that mean? You learned that to get the radiated field, you compute the radiation vector. And the radiation vector was the Fourier transform of your current density. Now I have 2 times the current density because they are basically at the same place because this d is so small. So for my folded dipole, I have 2 times the radiation vector of the dipole. I get as double amount of radiated electric field, basically. That's what I get out in these cases. So 2 times the current density, 2 times the field. So my folded dipole for the same current will radiate twice as much. That's what we have here. And now we'll ask you a question in these cases. So what's happening here in these cases here? So what we have in this situation here is the question what's happening with then the change of radiation resistance. So if I take this, I radiate twice as much field. How will that change my radiation resistance of the folded dipole compared to the dipole? So I make a poll here. I will open it for you very soon.
Can you repeat the question, please?
Yeah, so how does it change the radiation resistance you have here from the dipole to the folded dipole? So when you compare these two antennas, you compare the dipole, the folded dipole. Is it the same radiation resistance? That is A. Is it 2 times the radiation resistance? B. 4 times? C. Half? D. And a quarter? E. Those are the questions there. And think now, everything that you have learned in this course, how did we determine, for example, the radiation resistance for the dipole? If you think back, what did you do? You computed the total radiated power, and then you used that the current times the voltage, half of that, was the total radiated power. You know, the circuit, current since voltage is the power. And then you rewrote the voltage as the radiation resistance times the current. So the radiation resistance times the current squared is the total radiated power. Now I have the same current, I don't change that, but I radiate twice as much field. What will that do with my radiation resistance? So I launched this poll here, and to my understanding, that means you don't see the question anymore, but I will repeat it. A, the same, B, 2 times, C, 4 times, D, half of it, and E, quarter of it. Fill it out what you think would happen in these cases, and think what you've learned so far in the course. And as you notice, no advanced calculations, no integrals, just simple relationships that is happening in these cases. What do you think will happen in these cases? Okay, we got a little bit more than 50%, so a few more answers, please. Okay, so now I will end the poll, and then you will get to see the result there. So here you can see the result. Quite equal spread, but most of them came for C, which says 4 times the dipole. Then D, half of it was quite close, and a quarter, not so far away, and B also. C is correct in this case. It is 4 times the amount of radiation resistance you get. That is the correct result. So then we should understand why that is. Some of you who answered C, how did you argue that it should be C? Somebody wants to tell me how you were thinking about this case. Of course, if nobody wants to fill it out, I will fill it out for you. So in this case, you got 2 times the radiated field. What is power? Is the power proportional to the field, or is it proportional to the square of the field? Think again that you have, for example, a current or a voltage. When you get the power, yeah, it's the voltage squared or current squared, in this case, electric field squared. So that means that you got 4 times as much radiated power. Because you double the field, you square that, you get 4 times as much power. And then you have the relationship that the currents times the radiation resistance is proportional to the radiated power. The current is the same. You increase the total radiated power 4 times, which means you have to increase the radiation resistance 4 times, which means this one is the correct. So we really get these ones with 4 times. And you can see no hard calculations, but you need a deeper understanding, of course, what is happening in these cases. You need to understand those formulas that you've been using. And if you do this, yeah, we can actually see this is what will happen. And I will show you it happens for many cases. Now I can see it says a G there. That should, of course, not be there. So let's move on in these cases here. So as I mentioned, 2 times the current means that the radiated power is 4 times as high. So the folded dipole here radiates 4 times as much power. And the reason for that is, of course, that I said that the current there is equal to the current there. So with equal current is 4 times as much. And that's just the argument here that 2 times the field, 4 times the power, because the power is proportional to the field squared. The 2 squared is 4. And then you use this radiation resistance that is given by the voltage times the current, which is in that case the radiation resistance times the current squared. And if the power goes up 4 times, the current is the same. It means that the radiation resistance here has to increase 4 times. So now I increase the radiation resistance of my dipole 4 times. And then you can do the next calculations in your head. What was the radiation resistance for a half wavelength dipole? it was around 70, 73 ohms. Imagine it was 75. 4 times 75 is 300, which is pretty close to the twin wire. So by changing my antenna, I can start playing with these factors. I can manipulate my antenna to actually change its input impedance, or in this case, the radiation resistance. And foldering is one of those key principles to do that. It doesn't only work for this dipole. I will show you other examples very soon. But the basic physics there is the important thing to you to understand. So you can get the same radiation. The radiation patterns are the same for this. But the radiation resistance, very much different.
Excuse me, can I ask you a question?
Yeah, absolutely.
But don't we use like more power to feed the folded antenna?
If you were thinking about the total radiated power, yes, you would need to supply more power. But the quantity we are looking at here is the radiation resistance. And the radiation resistance is independent of the power you feed your antenna with. It's an antenna parameter.
Okay.
So what I have said here is that I assumed in these cases, to make the analysis simple to understand what's happened, is that the current there and current there are the same.
Okay, thank you.
But maybe I need to supply the system with a different power to keep the same current.
Yeah, that's what I'm thinking. That's what I was thinking. I was thinking about the trade-off.
Yes, absolutely. But if you then see what's happening is that when you determine the radiation resistance, it means here that you will change the radiated power, but you would also change the current as it's there. And your radiation resistance is the quotient between those two. So it doesn't matter. If you have to supply more current to get the same radiated power, it doesn't matter in these cases. Because the radiation resistance is independent on how much power you supply to the antenna or the current you supply it to. It's only depending on the metal that sits there in this case. So that effect disappears. Okay, I hope that answers the question. So let's move on with these ones. Now I will show you some of these folded dipoles. This is a typical what's called Yagi-Uda antenna. I mentioned it before. You've seen it on all rooftops, TV antennas, and so on. And if you look at the element that sits in the back here, this element here, that is the driven element. If you look at it, it's a folded dipole. So in many, many cases with this, you mix different types. So this driven element, in most cases, this is a folded dipole. The elements that sits around these ones, so elements here, these ones and these ones, they are what's called reflectors in these ones. And these wires here are directors. They push the radiation in a certain direction. They are not connected to the cable. So if you see the cable coming down there, it only goes to this folded dipole. So that is a typical use of these folded dipoles. In many cases, it's there. And as an antenna structure, yeah, it looks something like this. You just take your wire and you close it into a loop. We will soon study loop antennas, and we will see they behave pretty much similar to these ones. But they, of course, change in many other types of aspects in some ways. So the radiation pattern of this folded dipole, now I have no idea where this stands here. Oops, that should not stand here. It was probably a modification I did of the monopole, but I wrote it on the wrong place. Forget about everything that stands there. The dipole radiation patterns is the same for the folded dipole as the dipole. So if you look at this one in its radiation pattern, it really looks like this donut type shape that comes. That is what the folded dipole has. And the properties of these ones is that it's self-resonant when the length is approximately half a wavelength. And if you compare that with something, it's quite interesting because you can actually see that this is the circumference of the folded dipole, which is a loop. So if you think about the length of this folded dipole, it's half a wavelength plus half a wavelength plus 2 times d, and d is very small. So the length of the wire is actually 1 wavelength. We would see that when we come to loop antennas. They actually behave in a very similar way as these ones. And as I mentioned before, the radiation resistance increases approximately 4 times at the resonance. Away from the resonance, it behaves completely different. But at the resonance frequency, it's approximately 4 times. And it means you can easily feed this from a 300 ohms twin wire transmission line. So if you would like to use that transmission line, it's correct. You can use a dipole for it, but you need to use a folded dipole. So a slight change from what we did when we argued about this first. Very, very small differences. And this one works really well. And a typical use is this Yagi-Uda or TV antenna. So if you see those ones out on the rooftop or somewhere else, you can actually see that many of them have really a driven element that looks like this folded dipole. That typically sits in these cases. So this should also be a movie playing now, but unfortunately it's not. Maybe I will upload them to Canvas. So if you now take this folded dipole, so let's say that you drive this with the current, maybe you feed it over here. You can see in these cases at the resonance frequency, you can see here that it has a current that points in this direction and it points in this direction. So the currents are parallel, the points in the same direction. And that means that the radiated fields can be added up from them. If this distance here, let's say this is much less than lambda, so they're very close, then you don't see the slight phase change due to the distance between them. And the radiation pattern will look perfectly like from a dipole, because the currents are aligned, they point in the same direction. But now you start changing this. And if you think about your dipole, when you change the length of your dipole, the current basically behaved the same. Maybe it didn't look like a cosine, maybe it looked like a triangle, but it didn't really change it. Now let's change it on your folded dipole. Here you can see the current points this direction. Here it points this direction. Here it points this direction. And here it points this direction. What happens with the radiation from this one? Which I did now by just lowering the frequency or changing the relationship between the wavelengths and the length around it. If you start thinking about the pieces up and bottom first, so like this one and this one, of course, one points like this and one points like this. What happens with the radiation vector? Yeah, they basically cancel each other. So this will have a different type of radiation pattern. It will not look the same. This will not radiate like a dipole anymore. It will radiate as something completely different. And it will radiate like a loop. Yeah, Khalad?
Yes, but why if we changed here the frequency or the resonance frequency, the direction of the current differ here? Why?
So I'm not changing the resonance frequency. The resonance frequency is really given by this stuff here. But what I'm doing is that I'm lowering the frequency. So I'm not using the antenna at its resonance frequency.
So how did you know that the direction of the current should be at the assumed here direction, at the assumed direction that you said here before?
These are simulations from FECO. Of course, I could know where they go because I understand the antenna, but these are simulation results. They should actually be a movie showing how it's turning around there. So these are simulation results. And what you think what's happening here, a reason why you get these cases that this one points in this direction and this points in this direction. Imagine here that you send the signal from up here, and then you can calculate now what is the distance to this point here. How far away is that point? If it's now is one wavelength around that structure, I moved half a wavelength. That's how far I have moved.
Yes, yes.
And then you can start asking, what does that mean with the phase of it? It means it will change the phase. So actually, if you send away a current, let's say in this direction here, the current will move here, around here, and they will reach like this point here. And then you send the current, here you send it in this way. So it should go in the opposite direction. But you have to add the propagation length of this. And that's half a wavelength. That's 180 degrees, which means that actually current goes in this way. Because it's the distance around the structure that comes in. And half a wavelength is 180 degrees, which means it goes in the opposite direction. And if I do it on this very much lower frequency, if I send the current here, the current goes like this. Imagine here you can send like a DC current in a loop. The current just moves around it. There is no chance, because it's so small now, that its phase shifts will fix it for you. And that's where you get a loop in these cases. So it's an effect of this that we actually have structures on a wavelength scale that can change these things. So things will now happen, which is very different from the dipole. This will behave completely different from the dipole when I'm off resonance. When I was on resonance, it behaves like a dipole, except the radiation resistance increased. So if we look at this, we will have the same radiation pattern. Now we are at around resonance for it. So it looks like the same dipole type pattern as we had. But if I look now at the impedance for it, the input impedance, it looks like this. This is also simulated results. So you could run it in FECO. You have files for running a folded dipole in FECO. And you can see it's completely different what you had from a dipole. This doesn't look like a dipole at all, because it's only behaving as this real dipole at the resonance frequency. When you are sitting down here, it actually behaves like a loop. And if you think about the dipole, it was capacitive for low frequencies because you have separation of two metals. What did you have now? Now you have just a current that goes around it in a loop. That's an inductor. And this piece you can see here, this line here, that's basically J omega L. So the reactance, or the imaginary part of that, is proportional to the frequency, which is what we see there. It's a straight line that comes out. Here it starts happening quite a lot in the middle of these ones there. That's an anti-resonance, where actually the impedance basically goes to infinity or close to infinity, very high values. And what's happening there is that the current in your feed is very low. And that happens when it's half a wavelength around the structure, or approximately half a wavelength around the structure. And then here you have your regular resonance that we use. So that is where it starts looking like a dipole. And that's where it behaves as a real antenna you would like to radiate. And it has a reasonable value here of approximately 4 times this 70-73. That's what comes out. And then, of course, if I look at with matching, for example, the twin wire LED, yeah, it looks like a good match then. But in these cases here, of course, I have to have a very high impedance of the characteristic impedance for the transmission. It starts to go like that. So you can see now we start changing this, because now we get a little bit more like advanced antennas in some ways, but we can use what we have learned from it to actually also do these antennas. So that's a folded dipole. And now we will start looking at, okay, I changed the impedance of the antenna. And of course, when I have a dipole, maybe it's not enough, because, you know, the dipole is good, but we also learned that we need it to be around half a wavelength to make really work well. So here we will see what's happened, how we can shrink the length of it. And that will introduce first monopole and then actually miniaturized dipoles. So let's see what's happened at some typical frequency bands. So you are mainly used to gigahertz band, because that is the typical frequencies that are used in, for example, cellular communication today. So a few gigahertz, but there are many other frequency bands. One frequency band is what's called low frequency, LF. And those are radio frequencies here from 30 kilohertz to 300 kilohertz, which means that you have a wavelength in these cases from around 10 kilometers to 1 kilometer. And of course, you know, I have my favorite dipole here. How do you build your favorite dipole if it should be half a wavelength here? It should be at least 500 meters high. Is it fun to build something that is 500 meters high? Probably it's a lot of fun to build something that is that high, but it's not cheap. It's really expensive. The tallest human-built things are around 1 kilometer, skyscrapers built to like 1 kilometer. A structure here, which is called or was called the Warsaw Radio Mast, was for a while one of the tallest human-built things, structures on Earth. And that was actually 646 meters tall. And that was built to broadcast these frequencies here. So 126 kilohertz in the center frequency. A wavelength of approximately 1.3 kilometers. Now it really looks like, okay, it is half a wavelength. It's not really driven as a half wavelength dipole in this case. It's slightly off-centered feed and so on, but approximately you can think about it like that. So what's happened when you build something that is 646 meters high? What do you think will happen with it? You can look at one thing that says here. Obviously, this did only operate until 91. What do you think happened 91? It mechanically fall down. Actually, it couldn't take mechanics of standing up anymore, so it's actually collapsed. It fall down. Because of course, 646 meters tall is a lot. But that is what you need if you want to make something actually operating at these frequencies with the dipole. Because you need to build them half a wavelength. And half a wavelength at low frequencies is really, really strong structures. And of course, you can think, yeah, that's not so bad. We could build it. Then I say there are frequency bands that are called very low frequencies, the VLF band. And of course, a VLF band is even worse. Then you have wavelengths from 100 kilometers to 10 kilometers. It's a popular band for submarine communication. When you sit on your submarine, you don't really expect to download real-time YouTube or something and view it, because of course your bandwidth is basically zero. You send a few messages, you don't send a lot. You could see the same if you look at this Warsaw one, because you can see it had, in these cases, 2 kilohertz of bandwidth. Not much. But you could broadcast radio on it, and that's what it was used. So of course, a dipole is too long. I need to make my dipole smaller. GMS antennas, if you go back to the early history of cellular phones, you know, they look like this. What's sticking up there is basically half a dipole antenna, called a monopole antenna. And, you know, they were used these days. I'm old enough to have had one. And if you wanted them to be really good, you did like this. It might be hard for some of you, but I'm really mechanically folding out my antenna. Because these were operating here in the beginning at 900 megahertz, which had a wavelength of a little bit more than 0.3 meters, which means, of course, you don't really fit them well in your phone. The old phones, of course, here was quite big, so it was not a huge problem, the antenna. The rest was a larger problem. But we need to make these antennas smaller. We need to know how we should do that. So we really need to investigate ways to reduce the length of the dipole antenna. Because it's a good antenna, but it's too big. We need to make it smaller. So that is what we should do. We will soon take a break. We'll just go through first part of the monopole antenna. So the first idea to actually make it smaller is to cut it by 2. And that you can do by using these antennas here. So this is what's called a monopole antenna. And what you have with that is that you have your dipole sticking out here. That is your dipole, but it's only half of this dipole. So you only keep half of it. And then you use the bottom part here, which is the ground plane, or you replace the bottom part with this ground plane. So you put a metal below this monopole, and then you can start thinking, yeah, okay, I'm going to build something really big, and then I should put a lot of metal below it. That's not maybe so smart. Yeah, that's true. But in most cases, you have a lot of metal. Imagine a car. So the old types of all antennas on a car was basically a monopole sticking up from it. And it used the car as the ground plane. And you can do that with many different things. You can use it with a boat, for example. You can have a natural ground plane because you can take Earth down here as a ground plane. It's not a perfect ground plane, but it's a fairly good ground plane. A hard picture to see, but these ones basically have some wires sticking down instead. And that also forms some type of monopole dipole type structures that can make them slightly smaller in some ways. So what we're going to do now is, of course, that we're going to understand our monopole antenna. And to do that, we need to know what an image current is. So we need to know how we can remove the ground plane and replace it with other currents. And that we will continue with after the break. So let's take a break until 1/4 past, and then we will continue with this monopole antennas, ground planes, and then miniaturized antennas. And we move on from there. So with that, I will